do a lot of different things. I'm basically a complexity theory person with geometry tools. And of course, the funding landscape for complexity theorists with geometry tools or not is quite parched. So I do a variety of different things. As long as basically there's some underlying complexity theory and some geometry, I do a lot of different things. So this, on the other hand, I've been working on computational learning theory back for 10 years ago or something like that. But I more or less left the area at that time because it was basically theory. And since then, machine learning has, of course, taken off. And so recently, with two of my previous grad students, Mohammed and Menghan, we wrote a couple of papers, a few papers on using core geometric methods to actually give provable bounds on machine learning. So I decided I'm going to talk about that and see how far that goes. So this works, I guess. This should work. Oh yeah, so okay, that's that. And that's this. That's okay, I'll use this and I'll use this for the pointer. Okay. Oh, this went all the way to the back. Okay, there we go. So the problem I'm going to talk about is something called dictionary learning. I don't know, how many people have heard about dictionary learning? Yeah, okay. So this a little dense, but this picture should sort of make sense. So these blue things are all data points. So you're given a whole bunch of data points, and the goal is to express all the data points as sparse linear combinations of a certain number of vectors. So in this case, even though the dimension of the space in which the data points live happens to be 3, I pick 4 vectors, right? So potentially you can pick what is called an overcomplete basis, so more elements in your set of vectors than the size of the basis of the space, the dimension of the space. And the goal is to make sure that all the data points are expressed using, in this case, exactly 2 basis vectors, linear combination of exactly 2 basis vectors. So in this case, I've picked, for example, these 4 vectors as my dictionary vectors, and every one of the blue points lies on a plane spanned by some pair of these dictionary vectors. So the dictionary learning problem in general is given a data set in some dimension, and the goal is to find a dictionary with the property that there any number of dictionary vectors. At this point, I'm not concerned about how many. Typically, you want to minimize the number of dictionary vectors as well. At this point, I don't care. With the property that each of the data points can be expressed as a linear combination of the dictionary vectors. These are the coefficients. Sorry, D is the dictionary, the set of dictionary vectors. These are the coefficients. With the property that the number of non-zero coefficients is small. So that sparsity is also initially specified. So in this case, the sparsity would be 2, D would be 3, and N would be 4. Okay? So that's the problem. So the problem is to find the dictionary vectors with the given, so that every one of the input data can be expressed as a linear combination of the dictionary vectors in a sparse way. Of course, the problem is not the exact problem. In general, these guys aren't nicely sitting on the plane. There's some noise, quite a bit of noise. So you want to deal with the problem in general in an approximate setting. But I'm going to talk about the exact setting for now, because nothing is known in terms of bounds or anything for this problem. Right? Provable bounds for this problem. So So again here, this is an over-complete dictionary. By over-complete just means that the number of dictionary vectors is typically much, much larger than the dimension of the space. So, you know, M, which is the M is greater than N is greater than D is greater than S. So this is usually, this is the sparsity, this is the dimension, this is the number of dictionary vectors, and this is, I don't know, how can M be larger than N? Doesn't make sense. Oh, M is the number of, sorry, this is just the coefficients for these vectors, yeah. So dictionary learning, DL, I'm going to approximate that, abbreviate that as DL, is in a sense an inverse problem of the, if you have heard about this sort of standard dimension reduction problem, where what is given is, we already know the dictionary in that case, more or less, and we want to recover, because it's an over-complete basis, there isn't a unique way of expressing the vectors in terms of the dictionary because it's over-complete, but there's, what we're interested in is a sparse way of expressing the vectors in terms of this over-complete basis. So this sparse recovery problem is this problem of solving this heavily underdetermined linear system while trying to minimize the number of non-zero entries in the solution. So that's an NP-hard problem, and it's typically solved using, I don't know, this fashionable area called compressed sensing. I think a lot of, so what they use is a frame, what's called a frame, as the dictionary, so that you can get the sparse solution by just obtaining an L1, small minimum L1 solution instead of the L0 solution. So the L1 solution you can do using all these basis pursuit type techniques from statistics. So the L1 solution turns out to be pretty good for that case. Okay, the other sort of general approach to DL, sort of the usual approach to DL, is some kind of KSVD. So if you think of the original picture, oops, I'm going the wrong direction. So the original picture, SVD means essentially finding if all of these, if all I was given was one of these lines here, that would correspond to just finding one plane to which, close to which they are. But so that would be one SVD. KSVD would be generally trying to find K different. It's a kind of a K clustering approach. So that's the standard approach that's currently used for dictionary learning. And there are a couple of, how shall I say, variants of that. But there is no known guarantee of convergence to any kind of true dictionary. Okay, so there's been recent emphasis on provable guarantees for machine learning in general. There's an entire workshop with that name because there's it's very sparse, the number of provable guarantees for machine learning in general. So there was one algorithm by Spielman, which was then expanded upon by Agarwal and Arora, etc., which in this case he required the dictionary itself to be a basis. So in that case you want to find a basis such that the given set of data are sparsely representable, as sparsely as possible in that basis. They expanded it to non-bases, but then they expect the dictionary to be pairwise incoherent, which means, if any of you is familiar with this whole RIP or RIP matrices, essentially it requires pairs of columns to be nearly orthogonal to each other, right? So that's a very strict condition to be putting upon the dictionary. So just stepping back a little bit to the general question of provable bounds. Provable bounds in machine learning in general, not just dictionary learning. There's so dimension reduction, as I said, is sort of like an inverse problem of DL. So we actually, with my student Mohammed and we came up with this sort of approach to machine learning in general, which is some kind of a hierarchical sparse representation of data, which can then be used for classification or any other purpose that you would want to unsupervised learning. So that would be like alternating DL, DR, DL, DR. We called it the Durdle model. Okay, so and this appeared in, I'm sorry, I don't have the reference. It appeared in Brain-Inspired Cognitive Architecture conference. And so we had this, and we were promptly approached by, a letter was written to us by Jan LeCun saying, you did not cite blah, 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 you know, some 10 papers or something like this. So, and we just came up with that as a model for which we could try to prove something. That's the only reason we did this. This is completely feed forward. It's alternating levels of DR, DL. And we were trying to show whether or not more levels of this is strictly more powerful than fewer levels. Strictly more powerful meaning you cannot reproduce it using fewer levels without blowing up the size like crazy. We were unable to prove it, so we sort of gave up. And we then just concentrated on the DL part, which led to this paper that I'm talking about. And I had sort of a memory of an old nightmare, which I used to work on a long time ago, which was this question of weighted threshold gates. Okay, so threshold gate is just similar to a neural net. It's just a linear combination of the input set of bits, and you can think of it just as a characteristic, the characteristic function of a half space, right? So you have a hyperplane in dimensions equal to the number of bits of input, and one side of the hyperplane the function is 1, and the other side it's 0. So it's like a support vector machine type of situation. So each one of these gates it has arbitrary weights. It's unbounded weights, or weights that are not in any way bounded by the size of the input. They're not polynomially bounded in the size of the input. So this question is still open. So this question is open whether 3 levels of these weighted threshold gates are more powerful than 2 levels of weighted threshold gates, by more powerful I mean the same thing, that they cannot be simulated by the 2 levels using only a polynomial blow up. So in other words, no one has shown the type of result that you showed just before the lunch break, that in order to simulate 3 levels and 2 levels, you need an exponential blow up in size. Neither the positive result nor the negative result have been shown. Nobody knows the answer to this. And in general, nobody knows, sorry, this is not 2, this is k levels. I mean constant levels independent of the size of the input of polynomially many weighted threshold gates. Do they even compute all functions in NP? So this is sort of like the spectacular failure of circuit complexity, that we don't even know the answer to this. Okay, we don't have an exponential lower bound on the circuit size of unbounded weight polynomial threshold gates of constant depth, right? So we don't know if there's a traveling salesperson can be done with these or not, right? So there's this idea of not knowing whether more levels actually increases the power is, I think, very troubling in this today's world of deep everything, you know, deep learning and deep neural nets. So that's just taking a step back for a second. So I thought this was appropriate. So when nothing is known, you kind of feel free to do a lot of things. So I decided to work on some very basic versions of dictionary learning. So, and apply some of the tools of geometry, sort of standard tools of geometry, which I've generally used in many different places. So I'm going to work on a special case of dictionary learning which I'm going to call fitted dictionary learning. I'll explain it in a second. But before explaining how this relates to dictionary learning, let me just explain it to you as a geometry problem, right? So the geometry problem is that you're given the data points, think of them as pins, where you're trying to find a bunch of subspaces of a certain dimension, which is the sparsity, given sparsity S, with the property that this set of subspaces contains all the pins that are given to you, right? So you want to find a bunch of pins, given a bunch of pins, you want to find a set of points so that the points span a bunch of small dimensional, S-dimensional subspaces such that all the pins lie on those points. And the fitted version is one where, let's assume that you know which subset of points a particular pin lies on. So in other words, I'm given as input in this fitted dictionary learning problem a structure like this. And this is the simple case where S is 2. So in other words, every one of the pins lies on a line spanned by these two affine. Now I've moved to sort of the affine setting. So it's affinely spanned by these 2 points, and this pin is kind of lies on this line. So I'm given a bunch of pins, and my task is to find the pins' locations are known. So those are the data vectors that are given to you. You can think of them like that. And the goal is to sort of find these the location of these points with the property that this pin lies on a line that contains those 2 points, right? So the structure is, the goal is to position these black points in such a way that the given set of pins will lie on these lines, okay? So essentially that is the dictionary learning problem. The dictionary learning problem, one way or the other, comes down to this. The only difference here is that I'm giving you more information. I'm actually telling you which dictionary vectors give you the, for each data point, I'm telling you which dictionary vectors give the linear combination for that data point. So in the usual dictionary learning problem, no one tells you, hey, this data point, I'm going to express it in terms of these dictionary vectors, the identities of these dictionary vectors. Think of these as, let me see, maybe I have that picture. I had to cut this slides down, so I guess I threw that that picture away. Yeah, so you can think of it as, if you think of the dictionary, I guess we don't have a board. So if you think of the dictionary as columns of a matrix, then the dictionary vectors as columns of a matrix. So basically you can think of, you're trying to find the columns, you're trying to find those would be these vectors. You're trying to find the columns, but what you're given is, for each data point, you're given which subset of columns that data point is a linear combination of. Okay, so so those subsets are given. So once you do that, that becomes the fitted dictionary learning problem. So what you have, because of those subsets, are then sort of hyperedges of a hypergraph. So then the question would be, we're going to use some well-known techniques from what is an area called combinatorial rigidity, which is also related to matrix rigidity, which gives you, with the property that when we want to know when at least one solution to the dictionary exists, and when a locally unique solution to a dictionary exists. We can also look for globally unique solution. So what we can, so this is sort of like the first baby result, which even this was not known before, is to simply show that for very general data, so if I gave you random data, so your data comes from uniformly distributed on a sphere, randomly distributed on a sphere, then the size of dictionary that you need is at least the size of data, okay, with high probability. So already proving this required some work, right? So, so once we have such sufficiently general data, this gives you a very simple dictionary learning algorithm. And then we were also able to look at a bunch of other geometry problems that is related to dictionary learning, compare this approach with the existing approaches which I had in the previous slide. Okay, so the actual core of the talk is just this technique, really. How do you work with these hypergraphs, and how do you show that there exists, when there exists a dictionary solution for the fitted dictionary learning problem, and when there exists a locally unique solution, what is the characterization of that? Rigidity is a word for there exists a locally unique solution. By locally unique, I mean there could be another solution kind of far away, but in the neighborhood of this solution, it's the only one. So
the dictionary learning problem, is there a constraint on the number of vectors in the dictionary? I mean, otherwise the problem's
kind of trivial, it would seem. Yeah, in general, you would. So in this case,
B is at least omega x.
Yeah. So
B is an order of x, isn't it? Sort of.
That's what this is saying. So this is saying that if you really want to if your data is randomly distributed, you're not going to get any better dictionary than the size of the data.
So just each point is a dictionary.
You can essentially have, I mean, this is omega, so you can get some constant, a certain constant improvement, but other than that, you can't do it. So in other words, dictionary learning is only meaningful when you have very structured data. Okay, so so this is the key part of the talk, and I'll try. I know it's after lunch, and I'll try to. It's kind of heavy, but I'll try to go. I keep forgetting. Yeah. Okay. So this is the main result. We already did that. Okay. So this is the property of the hypergraph. So let me explain some of it. D was the original dimension. S is the sparsity that we want, and so you have an underlying hypergraph where E is the set of edges of the hypergraph, or hyperedges of the hypergraph, where E corresponds to the number of pins. So each pin, or each data point, represents a hyperedge, namely the hyperedge connecting that involves the subset of dictionary vectors which are involved in the representation of that data point, right? So essentially, E, the size of E is the size of the number of data points. So this has to be true. So we showed that the main result basically shows that for the fitted dictionary learning problem, we have at least one solution and a locally unique solution if these conditions hold. Okay, so the first condition relates the number of dictionary vectors, which is the points, and which is the black points in that original figure, and E, which is the number of pins or data points. And the same condition has to be true for every subgraph of that hypergraph. So in other words, if I look at any set of data points, any subset of this dictionary matrix, the same condition should continue to be true, except with an inequality. So as long as this is true for every vertex-induced subgraph, and this equality is true for the whole thing, then we can actually show that these things hold. So if I want to find unique, if this is also an inequality, the same inequality is here as well. So in other words, I get rid of the first bullet and simply use the second bullet for every vertex-induced subgraph. Then that would give us at least one solution, right? But this equality here is necessary to get a locally unique solution for the whole thing. So this is sort of the terminology in combinatorial rigidity literature. So here's an example with, this is just showing an example here with the size of the dictionary. In this case is 4, because there are 4 of these which we're trying to find, and the size of the data points is 6 in this case, right? So the d equals 4 and s equals 2. So this would be the kind of structure. This is the combinatorial structure that's given to us, and from this we have to sort of determine, using those combinatorial conditions that I wrote down. We want to show that those combinatorial conditions essentially correspond to the existence of a solution. So the existence of a solution is sort of like an algebraic thing, but the conditions are sort of purely combinatorial, kind of counting conditions in here. These are just some kind of counting conditions, but this is sort of seems to depend on the actual positions of the data points, but we can show that these counting conditions are sufficient because we have this assumption of genericity, or randomly positioned. Okay, so the general sort of cottage industry in combinatorial rigidity goes through these steps. So you write the algebraic problem of finding the solution for the dictionary vectors using the given data points. You then show that the existence and local uniqueness of solutions corresponds to the full rank of a particular matrix, which is the Jacobian of that original algebraic system. So you linearize. It turns out that the algebraic system is quadratic, in this case bilinear. And once you take the Jacobian, you end up with a linear system. So we show that the existence and local uniqueness then corresponds to sort of this linear system having full rank. And then we go and characterize the hypergraphs for which this rigidity matrix, which only depends on the hypergraph, ends up having full rank, okay, in a generic way. So this rigidity matrix is really a matrix of indeterminates. If you think of the pins as indeterminates, without actually giving exact positions, and we can do that with the indeterminates, more or less like what she was doing, Muriel, when she was talking about, when you take when you do this randomization, then you end up with just with the purpose of having these Edmonds matrices whose determinants do not vanish, right? So which you can assure yourself with the Schwartz-Zippel lemma, so that in general, most of the time, this determinant is not going to vanish. Same thing, generically speaking, we can argue that the vanishing of this determinant comes down to a combinatorial condition. So the non-full rank of this comes down to a combinatorial condition, or vice versa, right? So, and matroids play a big role here too, just like in the other case, right? In that case, it was the Edmonds matroid, the network flow matroid, the bipartite matroid. In this case, it's a different matroid. It's a much harder beast. Okay, so now what is the algebraic representation of this? So the problem is finding the common solutions of a system of polynomial equations. A data point pin is incident on the subspace that's spanned by a bunch of dictionary vectors. You can simply write it as the S by S minors all being 0. If a data point has to be on a space spanned by the vectors, you can simply say that somehow the volume of the simplex that's formed by the data point together with all the dictionary vectors sort of gets squashed down to 0, right? So the volume squashed down to 0. So that's all it is, saying that these minors vanish. So each pin therefore gives that many equations, and so you can simply write the equations down. So all the equations come down to saying all of these subdeterminants, which corresponds to volumes of simplices, all vanish. Okay. So So the fitted dictionary learning basically comes down to solving a large system of polynomial equations, each row of which corresponds to some determinant vanishing. And then, so without any pins or data points, the n dictionary vectors have this many degrees of freedom. Every potential pin removes that many. This is sort of like an intuitive way of understanding why we end up with those numbers, right? So you can think of again, this is just writing the framework. It's called a pin subspace incidence framework, which is a purely combinatorial objects. These are the pins. These are the data points. Sorry, the pins are the data points. This is the dictionary vectors, and this is the hypergraph. So you can think of, this is the given set of pins and so forth. This we already did. I don't know, this sort of misplaced slide. So this is sort of the rigid, just means at most finitely many solutions or locally unique solution. This minimally rigid if it's both independent and rigid, and independent just means you actually get generically a solution. Okay, so to the existence of a solution in this case corresponds algebraically to all of these polynomials that we have. We have a polynomial system. We want to show that polynomial system generally has a solution if none of them is in the ideal generated by the others, sort of, and these are just equating these rigidity terminology with the solution, existence of a solution terminology. So then the goal then becomes characterizing minimal rigidity of this system and of the framework. So the challenge is, of course, checking dependence on a set of polynomials, and this is where, in general, this is extremely hard. This is more than double exponent, 2 to the n type of complexity. So that's why we do the linearization into the rigidity matrix. So the combinatorial rigidity approach is reduced to linear dependence, so full rank of a certain matrix, and there's a key theorem which is showing that in general the dependence of this polynomial system reduces to dependence of this linear system in the generic case, and it's called the Bolker-Roth theorem, which is a famous theorem which basically shows that. And so the rigidity matrix of a framework is a matrix whose kernel is the motions. You can imagine this pinned subspace framework actually moving. If there are local motions, then it corresponds to locally the solution is not unique. And so you can think of the rigidity matrix right kernel sort of expressing these motions, and the rigidity matrix left kernel, for those of you who know something about statics, corresponds to the stresses of this framework. So that's another sort of geometric or intuitive picture, so that you can imagine this pinned subspace incident framework actually moving if there is a non-zero, if there is no locally unique solution. So you can take the Jacobian of this system, and this is just an example where of taking the Jacobian of this system. I'm not going to go through this. This is too painful at this time of the year, at this time of the day. Okay, it's more like a class lecture notes. And so if we choose a d minus s rows of this hyperedge for every hyperedge in the original system, a hypergraph, then the obtained matrix is a rigidity matrix of this size, and the framework is infinitesimally rigid, or in other words, has a locally unique solution if and only if there is a submatrix of full rank. And that's the sort of first lemma, right? That the infinitesimal rigidity is the linearized rigidity, or the linearized existence of a locally unique solution. And this is basically showing that the linearized existence of a locally unique solution is identical to the actual existence for this polynomial system. under the condition of genericity, right? So we can characterize the genericity framework by simply looking at the rigidity matrix, and that's how the rows of the rigidity matrix give us this matroid. The dependencies of those rows are then the circuits of the matroid, so it's something called the generic rigidity matroid, and that's how we get the combinatorial characterization. So then we get this combinatorial characterization by looking at this matroid, and this is what I had in the previous slide. How do we prove this? We prove this by taking what's called a TUT, fairly standard technique of taking a hypergraph and drawing. There's a notion called sparsity or tightness. So we first produce a sort of a slightly expanded expanded hypergraph to the original hypergraph. This is just a graph, but in general this could be a hypergraph because each one of these pins could be dependent on more than 2 data points, right? More than 2 dictionary vectors. Sorry, each of the data points could be dependent on more than 2 dictionary vectors. So this, what is drawn as an edge here, could generally be a hyperedge. But we produce a sort of a hypergraph, multi-hypergraph here, which weights each of the hyperedges depending on the size of the hyperedge in some sense. And there's a nice theorem by Tutt-Nash, which was extended a little bit to talk about tightness instead of sparsity. There's a Tutt-Nash-Williams theorem that says that we get this kind of sparsity condition. This condition is called this combinatorial condition that I had before. Hang on. This combinatorial condition is basically a tightness condition because you have here exact equivalence, and this is a sparsity condition because you say that for every sub-hypergraph the number of edges is at most something times the number of vertices. So this is a sparsity condition, this is a tightness condition. So we can represent the tightness condition as a decomposition into k-edge disjoint, what are called map graphs of the original graph. So the tightness condition becomes a decomposition into map graph condition, and the decomposition into map graph condition gets converted into a rank condition on the original matrix. So that's the general strategy of the proof. So we want to prove that this sparsity condition or tightness condition corresponds to generic minimal rigidity, which means full rank of the rigidity matrix. So we want to get something about rank from some counting condition here on the hypergraph. And to do that, we do it in 2 steps. We first convert the rank, this sparsity condition into a decomposition of the hypergraph. Oh, I'm surprised it didn't happen so far. And then from the decomposition condition show that the corresponding matrix has full rank. So this is the 2 steps, right? So this part is the first part, which is just getting the decomposition into hypergraph, for which we use the Tutt-Nash-Williams. And then the second part is to, well, we haven't come to the second part. We have to adapt Nash-Williams a little bit. And that involves sort of directing these edges. So these are not just edges, they're sort of directed edges. And we want the Tutt-Nash-Williams decomposition with an additional condition on the arrows of this hypergraph. That's the only, that as far as I can tell, everything else that we followed was sort of a very standard way of doing combinatorial rigidity proofs. Especially for these general geometric systems, which was done by 2 people called White and Whiteley. The references are at the end. White, by the way, was a faculty member here in the math department who did Grassmann-Cayley algebra and things like that, which fed into a lot of the initial proofs of some of the theorems that we used here. So then from this we can show that, So we can get the tightness or sparsity condition to be equivalent to decomposition into these map graphs with the tail additional condition with the arrows. And then we can show that if the map, once we get this decomposition, we get the matrix to not have determinant that's identically 0. So to get this, we use the Laplace decomposition of that matrix, and have to show that generically speaking a bunch of determinants don't vanish, right? So at the end of this we end up with this corollary that if you give a set of points that are picked uniformly at random on the sphere, a dictionary D that S represents has at least this much size with probability 1. So then you can ask yourself, okay, you're telling me that, you know, with random points, you know, there's no hope of really doing dictionary learning. It's a negative result, okay? So what is it that you can do? So that leads into, no, before that. So in this case, where you actually give me a small number of points, is a very cheap and very simple algorithm to find the dictionary based on the results that we have, right? And it's a constant, almost a constant time algorithm to find the dictionary. So then we talk about the related problem. So in general, you do not have, so that means dictionary learning is meaningless if you give me random points. They have to be highly structured. So if they are highly structured, then what are the sort of stages that you would go through before you use our techniques, okay? So these are all, we just wrote down a bunch of sort of formal problems, and we went to see if any of these had been solved, right? I don't think any of these has been solved. So if you're given a data set and a number k, can you find any subspace arrangement such that all of these lie on here? So I'm not asking you for the dictionary vectors. All I want is a bunch of subspaces that basically covers all the given points, subspaces of a certain dimension. I don't even bother to give me the dictionary vectors. And then, because the minimum number of dictionary vectors will presumably lie in some judicious intersections of these subspaces, right? Which I'm not even asking about. So then this is that problem of actually finding a smallest spanning set for a given subspace arrangement. So first you find the subspace arrangement, and then you want to find a set of points which spans all of the subspaces. So you want to minimize the number of points that spans all of the subspaces. Neither one of these problems is solved, and both of them have been looked at. Okay, so in both in algebraic geometry, people look at these subspace arrangements, and they've also been looked at in computational geometry, but not easy problems in general. So our strategy would be, you know, in this case would be you would first learn the subspace arrangement, and then you recover D by finding the smallest spanning set of this. And then we can use, so once we learn the S subspace arrangement, then we basically have converted into a kind of fitted dictionary learning problem. And so these are some other problems which, because usually you don't have a unique solution, so you can always talk about a notion called support equivalence, which adjusts for this. So you have another problem which essentially says that if you have data that are partitioned into support equivalent classes, then what is the minimum size guaranteeing that there's a locally unique dictionary, and how do you find such a dictionary? So this I think we nearly have solved right now, but this is sort of a general table of the different techniques that exist, and so this tells you the techniques here, and this is sort of the conditions on the data. And so this input conditions, in this case, you know, you want to get minimum size dictionary guaranteeing local uniqueness. And these are sort of different types of approaches. These are the only two that have any kind of proofs as far as I can tell. So this sort of says what you want, right? The conditions that you want. So in this case you have some results, as I said, but the conditions that you have are pairwise. In this case, it has to be a basis, so D is a basis. In this case, the dictionary vectors have to be pairwise incoherent. And then once you have, if we do it in this two-stage process, you first find subspace arrangement and then you find a spanning set. Then finding a minimum M is unknown, which is the only useful thing in this case. We don't know that. And then this would be the case where you have that support equivalent or segmented data. And in this case, again, important things are not known. And then finally, we have our situation. One of these we have filled, I think. This I think we have filled now, which was the previous slide, the problem in the previous slide, which we have something of a solution for right now. And then this is the case of fitted dictionary learning, which I talked about today. And we have a straightforward algorithm, but in the case where you have dependent data, we don't know what situation to use. So these are sort of pictures sort of representing these kind of the classes of problems that these different algorithms deal with. So I think the way to think about this talk is, since almost nothing is known, you have to start somewhere, right? As similar to looking like a 3-node problem or something, So you have to start somewhere, and there are certain tools which appear to be, certainly geometrically speaking, the problem is almost identical to solving the dictionary learning problem, if you appropriately split it up into parts. Now, as to whether the geometric techniques are the best to use for this problem, or whether to just use some kind of very general statistical method like KSVD or something, I don't know. I can't answer that. Yeah. But one thing is that these general statistical methods don't really give you very, it seems like it's hard to even characterize what properties the data should have for them to work properly. Yeah. Any questions? Okay. Yeah, she has a question.
Sure, this is a very naive question. So have people looked at things where you're just trying to reduce some sort of, maybe get something approximate with some error?
Yeah. I don't think that will change the basic lower bounds. Yes, yeah. But the SVD methods don't care, right? They don't care. Our method, which I have, here are some of the, just go through this just for completeness. So this is White and Whiteley, by the way. And so let me go back. So this method that I had here, so this simple method, this adapts. This definitely adapts to any perturbations that you might have to the data. It's a very, so embarrassingly simple method under the condition that you have points that have been, uniformly picked. So this definitely adapts even if the point is not definite on the subspace. It's somewhere close to the subspace. And the new algorithm, which I didn't talk about, which uses this idea, where is it? Going the wrong direction. So it uses this idea of support equivalence, and that support equivalence is exactly built for this purpose, yeah. And this algorithm also loosens the genericity condition, so you can have many points lying on the same subspaces, so it doesn't look random at all, right? And that also works, right? Except that none of these, first of all, this is for the special case of fitted dictionary learning, so someone has to initially tell you this hypergraph structure beforehand, So as to how to derive the hypergraph structure from the general problem would require solving one of these problems first. Yeah.
It's getting late in the day.
Yeah.
People have to respond to the questions. But then, thank you again.
Yeah, you're welcome. Thank you. Thank you. Yeah.
So my next speaker is my mate, Ken.